You're listening to Spacetime with Stuart Gary.
In less than a week from now, the European Space Agency's ExoMars entry, descent and landing module Schiaparelli will touch down on the frozen, arid surface of the red planet. The cone-shaped Schiaparelli lander was launched on March the 14th, attached to ESA's ExoMars Trace Gas Orbiter or TGO spacecraft for the 7-month journey to Mars. On October the 16th, just 3 days before reaching Mars, Schiaparelli will undock from the mothership and make its own way to the planet's surface, with the TGO then changing its trajectory and undertaking a critical Mars orbit insertion manoeuvre on October the 19th in order to enter orbit around the red planet. During its 3-day coasting to Mars, the Schiaparelli module will remain in hibernation mode, pretty well where it's been for most of its 7-month journey so far. Hibernation mode is designed to save the energy of its batteries. About an hour before reaching Mars, Schiaparelli will wake up and its onboard computers will be switched on to prepare the spacecraft for EDL, that is atmospheric entry, descent and landing. This will include the startup of the telecommunications system, the inertial measurement unit including its accelerometers, gyroscopes and radar Doppler altimeter. In addition, the propulsion system designed to slow down the spacecraft before landing will be prepared by ensuring the correct operating temperature of the equipment and by opening valves to allow propellant to flow from the tanks to the thrusters. A dedicated sun sensor on the back shell will then be used to recalculate the 777 kilogram lander's orientation before it starts the entry and descent phase. The information gathered during the 6-minute journey to the red planet's surface will test a whole range of new technologies designed to deliver a lander or rover safely to the Martian surface. These include a new heat shield, a new parachute system, a Doppler radar for altitude and relative velocity measurements, a telemetry tracking and command system, a liquid propulsion system for attitude control and final braking, and finally a crushable attenuation system to physically cushion the landing. The blunt-nosed module includes a 47-degree conical back shell and a 70-degree cone-shaped front heat shield designed to handle temperatures of up to 1,750 degrees Celsius during atmospheric entry. The aeroshell comprises a sandwich structure of carbon fiber reinforced polymer skins and aluminium honeycomb. Schiaparelli will enter the atmosphere at an altitude of about 120 kilometers above the Martian surface, traveling at a speed of 5.83 kilometers per second or 21,000 kilometers an hour. Protected inside the aeroshell is the surface platform, which carries the main spacecraft systems and electronics, as well as a small scientific payload conducting environmental studies during its short mission life of just a few days on the Martian surface. Atmospheric drag will slow down the speed of descent drastically, and when it's travelling at about twice the speed of sound, the craft will deploy its 12-metre diameter parachute. As soon as the module stabilises beneath the parachute, it'll jettison its front shield by means of pyrotechnic electro-explosive bolts, allowing its Doppler radar to begin sending back data on the spacecraft's altitude, vertical and horizontal velocity. Then, at an altitude of about 1,000 metres and at a speed of about 70 metres per second, or 252 kilometres an hour, the surface platform will separate from the back shell and parachute, and the 9 CHT-400 hydrazine thrusters will begin firing to further slow down the spacecraft and dampen its horizontal and vertical motion. The thrusters will shut down just 1.5 metres above the surface, allowing Schiaparelli to simply drop to the ground at an impact speed of about 4 metres per second, or 14 kilometres per hour. This approach ensures that the plumes from the thrusters don't disturb the ground and also avoids the possibility of an unstable landing on a rocky surface with the thrusters still functioning. The cocoon holding Schiaparelli's surface platform is some 2.4 metres in diameter and 1.8 metres high. Once on the ground, the landing platform will be just 1.7 metres wide. Schiaparelli carries numerous engineering sensors designed to monitor the performance of the spacecraft during its entire entry, descent and landing sequence. Other sensors will measure temperatures, heat flows and pressures on both the front and back shields, orientation and deceleration during flight, and finally the deceleration of touchdown. All these data will be relayed back to Earth either through the TGO orbiter or the Mars Express orbiter, as well as through the various NASA spacecraft now in orbit around Mars. This will allow engineers to reconstruct the flight in a simulator so as to optimize the technology and flight processes needed for future missions to the red planet. Schiaparelli is the European Space Agency's second attempt to land on Mars. The first was the Beagle 2 lander, which travelled on the Mars Express orbiter, which launched in June 2003. After being deployed from Mars Express in December 2003, Beagle 2 began to descend towards the surface. However, all contact was suddenly lost prior to landing. In late 2005, Beagle 2's inventor, Professor Colin Pillinger, released specially processed images from NASA's Mars Global Surveyor spacecraft, which seemed to suggest that the lander had touched down in a crater near the Ascidius Planeta landing site. It was claimed that these blurry images were showing a primary impact site as a dark patch, and a short distance away, Beagle 2, surrounded by deflated airbags with its solar panels extended. However, all that was put to one side when in January 2015, NASA's Mars Reconnaissance Orbiter spacecraft spotted Beagle 2 intact and safely on the surface, but with two of the lander's 4 solar panels failing to deploy and blocking the spacecraft's communications antenna. Finally, the mystery had been solved.